My name is Mr. Mats. Welcome to my YouTube channel. Please subscribe and also share and like my video. So you are given this question: sketch the graph of the function. This is a calculus question, and we are going to sketch this equation. So the equation is y is equals to x raised to power 4 minus 4x raised to power 3 minus 10x minus 5. So for us to sketch this graph, first of all, you have to identify the critical points. The critical points is going to help us also to find the interval where the function is increasing or decreasing. The interval, if it is increasing or decreasing. So it also going to help us to find the extrema, that is the minima and the maxima. So we also are going to find the possible point of inflection, and the possible point of inflection is going to help us to find the concavity. We have two types of concavity. We have the up concavity and the down concavity. So, and also we are going to find the possible point of inflection. So these points are going to help us to sketch this graph. So I'm going to take you through the critical point, and to find the critical point is the derivative of the equation. In short, is the first derivative of the equation, and we equate it to 0. So the dy of this equation, we are going to equate it to 0. When you find the derivative of the initial equation, you are going to get it to be 4x raised to power 3 minus 12x raised to power 2 plus 10, and we are going to equate it to 0. So when you equate it to 0, it forms as a cubic function, which we are supposed to solve for the value of x, which are going to be the critical points. But for a cubic function, we cannot use a quadratic method, because the quadratic method is only used when the highest power of degree is 2. And here we can see the highest power of degree x is 3. It cannot be used. Neither can completing square nor factorization or polynomial be used in this case, but we are going to use a new special method that is called Newton's Raphson method. And this is how this method states. This method states that xn plus 1 is equals to xn minus first derivative of the function of xn divided by the second derivative of the function xn. This is what it states, where xn is the current guess, xn f prime, that is the first derivative of xn, and f double prime is the second derivative of the current guess, that is xn. So the question that we are going to ask ourselves is, how do we do or guess the guesses, the current guess? How to guess the current guess? We are going first to find the second derivative. So the second derivative, that is d2y of divided d2y over dx squared. When we find the derivative of this equation and equate it to 0, we find it to be 12x raised to power 2 minus 24x is equals to 0. Now, that was the question which we asked ourselves. How can we find the guess? Because this is a cubic function. And this it is possibly going to pass in the x-axis. It's going to give us around 3 possible points where it can pass in the x-axis, and we are going to use an app called Well-From, where we are going to use the function, the first derivative, and equate it to 0, and we are going to compute this function equated to 0 in this app. This is a graph app that is going to give us the possible guesses. And when we have this in that app, it's going to give us this as the guesses: -1, 1, and 3. So when you have the guesses, now you can apply the Newton-Raphson method. And this is the Newton-Raphson method as we had seen. So we are going to start with the first guess, that is -1. and you are going to do this iteratively, that is procedural, until you find where the value of x, the output xn plus 1, is converging, seems like to converge. So when we have 1 there, we find the value of the output. You replace the equation to the -1 minus the you replace the value of -1 to this equation, this one, and you find the value to be -0.8333. So when the value of output which you have gotten, you are going also to use it as now the current guess. So you are going to use it as the current guess, and you're going to input it to the function, and you're going to get -0.804. I forgot to include 04. That is -0.8104. This is an approximation to 4 decimal places. So we are going to repeat this procedure until you get where the value is converging. And when you repeat this procedure, you get that it is converging around this figure. So this is the possible critical point that I've approximated it into 2 decimal places for easy doing. So we shall proceed to the next guess, that was 1. So when you compute 1 to that function, to the function of the Newton's method, when you compute 1, you get the output to be, the first output, when you have 1 here, you get the output to be 1.1667. So this is going to be the current guess for the next input. So when you input this function out of the equation, you do it, you are going to get this as the value of the output, and this is going to be the current the next guess for the next Newton's method. So when you apply it here, you get the value of the output to be this. As you can see, these two points are converging. So these 2 points are converging. So this is possibly the critical point. So the critical point when the guess is 1 is 1.168. So you're going to go to the third guess when the guess is 3. So when the guess is 3, the first output is 2.722. Now I know you have understood how we go about that way, and we're going to use it at the next guess in the second Newton's method. And when you input it, you're going to get the value of it to be 2.648. So we will repeat. When you repeat, you will get the same value to be this one. So this is the critical point. So we have 3 critical points in this equation, and these critical points, the first one is -0.8104, the next one is x is equals to 1.168, and the next one is x is equals to 2.648. These are the critical point for this function. These are the critical point for these functions. So now we are going to see how these critical points are going to help us to find the interval. For we had said in our earlier discussion that the critical point is going to help us to find the interval where the function is increasing or decreasing. So these critical points are the ones that are here. These are the critical points. So we are going to find the interval. These are the value of x. So we are going to have the x axis. So this is the x axis, and these are the values. You have this point, you have this point, you have this point. So we are going to find the interval between from -infinity up to this point. What is the nature? Is it increasing or decreasing from this point up to this point? Is it increasing or decreasing from this point up to this point? And finally from this point up to this point. So you are going to take a number that is from -infinity up to this point, and I took -1. So when you have this -1, you replace it to the first derivative equation. So when you replace -1, you are going to get a negative. You are just interested with the sign of the final answer. If it is a negative, it's a negative. So this is a decreasing interval, and the decreasing interval is represented by a fall, a vertical, a diagonal vertical, I'm a diagonal. So we are going also to this point and this point, that is negative 0.18 and 1.68. What is a number that lies between this point? One of them is 0.5. I use 0.5, but you can use any that lies between this point and this point. So when you put this to this, the first derivative equation, you get the final to be a positive. The output is a positive, and a positive is represented with this diagonal. So you also continue the process between this point and this point. I took 2. I found it giving a negative. So this is the nature, that is a decreasing. And from now this point to infinity, I took 3, and I found the output to be positive, and it is an increasing interval. So after I have found this, we said also a critical point is going to enable us to find the extrema. So how do we find the extremas? So that is the next look that we are going to see. How now do we find the extremas? The extremas are gotten from the second derivative. When the second derivative of x, is less than or is less than 0, that is a minima. When the second derivative of x is this is greater than 0 is a minima, and when it is less than 0, it is a maxima. So that is what you are going to help us to find the minima and the maxima. So you are going to take these critical points, these ones, and replace them to this second derivative function, so that to find the value of the output. If the output is greater than 0, that is a minima. So I took this point and output it to this point where there is x, and I found the output to be this one. So this point suggests that it is greater than 0. So this is a minima. When you take 1.16, is going to give us negative 11. This is less than 0, is a maximum. And we take the final point, that is 2.648. It's going to give us an output of 20.56. That is greater than 0. That is a minima. So we have finished evaluating the critical point, where it has given us the interval and the extremas. Now we are going to find the possible points of inflection, and the possible point of inflection are gotten by the derivative of the second derivative. And also the second derivative, when you have found this, the possible point of inflection is going to give us a concavity. So when you find the second derivative is this one, 12x minus 24, which is gotten by the first derivative, that was 4x raised to power 3 minus 12x raised to power 2 plus 10. So when you differentiate this to the second derivative, that is d2 of the x squared, you will get to be 12x power 2 minus 12x. So this is the, and equated to 0, this is that is the derivative, the second derivative. So this second derivative is going to help us to find the concavity. So when you evaluate the value of x, you find the first value of x to be 0 and the second value of x to be 1. So these 2 points are the possible points of inflection, and we are going to evaluate the concavity between these 3 points. So these are the x values. So you are going to draw an x-axis where we have 0 and 2. But you have a point that is from negative infinity to 0, and between 0 and 2, and from 2 to infinity. So you are going to evaluate the concavity between those points. So a point that is from negative infinity to 0, you can pick any. So I decided to pick 1. So when you evaluate this one and replace it to the second derivative equation, the final output, you are just interested with the final output, it will be a positive. And this is a upward concavity. When you replace, you take a number between 0 and 2, I took 1, and the final output was a negative. So this is a downward concavity. So when you take 3, that is going to give us a positive as an output, and it's going to give us an upward concavity. So now we have found the concavity, the interval. Now we are going to find out the coordinates of each points of x. That is the x coordinates which you have gotten from the critical points and the points of inflection. We are going to find out the coordinate of the y. So we are going to find the coordinate of these points, that is x is 0. These are the possible points of inflection, and these are the critical points. Now we are going to find the y outputs of each. So the y outputs, we are going to replace each point to the normal equation, to our first equation. So when we replace 0 to the first equation, you get the value of y to be 0. And when you equate a negative 0.81 to our initial equation, you get the value of y to be negative 1.14, and you continue this process, and this are going to be the outputs of y for each point. So now what is remaining is to sketch this graph, and this graph is going to be sketched. We are going to evaluate each point based on the interval before it and after it, and the concavity before it and after it. So this is the critical points, and be attentively here, my students. So as we had seen early, these were the coordinates which we had gotten. So these were the coordinates which we had gotten, and this was the interval. This is the concavity sketch. But this is the x axis. So this is the interval concavity. So you are going to use these intervals, and also you are going to use this concavity and this interval to see the nature of the graph before the points and after the points. So first of all, we are just going to sketch the graph, and this is the sketch. So at this point, this is where we have negative 0.81, and I'm going to write it to 2 decimal points, and the negative 11.40. So you are going to evaluate, and I'm going to show you how I came with this kind of sketch. So from the interval here, you find this is a down-going graph because the output was this way. So you saw, no matter where it starts from, any point is going to slope downward, and that's why I sloped downward up to that point. So when we reached at that point, I stopped. So the next point that I'm going to sketch is 0, 5. So I'm going to sketch, this is 0, 5. So 5 is between 4 and 6. So this is 0 and negative 5. So what is the nature? From the interval, 0 is not recorded, but from the concavity, we have 0. That from any point before 0, it is a upward concavity. So we are going to sketch an upward concavity. So we are going to continue with this kind of graph. So you see, up to this point is representing an upward concavity that is this way. So you can see it's an upward concavity up to that point. So the next point that we're going to plot is this one, 1.168, 2.16. So this 2.16 is around this point. So this is 1.168, 2.16. So that is around that point. So you are told we are going to see what is the nature. So this is between, but before we reach at this point, we have this point between this point up to that point. What is that nature? The nature is, it is upgoing. So we are going to upgo. See, we upgo up to that point. So we have reached up that point. Now we are going to evaluate from this point. We have reached at that point. Also, we can look at the concavity. The concavity between 0 and 2 is a downward. So between 0 and 2 is supposed to give us a downward, and you can say this is a downward concavity. Is a downward. It's going this way. It's a downward. So up to this point, you have reached this point, and also now the next point is 2, -1, 2, -1. So this is 2, -1. This is -1 around there, then that is 2. So what is the nature now from this point up to this point? Up to this point, when you go to the interval, you are told from the concavity is downgoing, so it's supposed to go downward. So it's going to slope downward so that it can form a concave down. So there's a concave down up to that point, as you can see. Now we are remaining with one point, that is between this point. Between this is point 2.648 and -3.62. So this is the point. So what is the nature now from this point up to this point? You know, this I had drawn prior. Now I'm showing you how I came up with this kind of sketch. So let's evaluate from this point up to this point. So when you go to the interval, you're told from 2 to from 1.168 to 2.648 is supposed to be a downward going sketch. So you see, that's why it's going downward. So after 2 onward is an upward sketch. See, after 2.6 and onward to 3 is an upward sketch, but we don't have the next point. And also the concavity states that from 3 is supposed to go a concave down. So that is what you can see. From this point is going to be a concave. This is going to be continuous. This is going to be continuous. So this is how the final answer was supposed to look like. When you're told to find the local minima, this was going to be the global minima, and this is going to be the local the global maximum, while this is going to be the local minima. So thank you for following through. If you have any question, any comment, please kindly have your comments down there so that I can go through them and maybe clarify and point